Okay, so we've already marked your individual code for the linear regression project. So the code is available under linear regression project and then submissions. So I encourage all of you to look at each other's submissions. So now we're just gonna go through like a Marcus report of the entire task in general. So just to recap, for task number 1, Eason gave you all a generator function that can be found if you go to his home folder and the generator function will basically yield a random x and a random y that follows a uniform distribution that is about a certain predefined gradient and a certain predefined y-intercept. Okay, then the task was for you guys to create a linear regression model to approximate this relationship. So what we noticed is that after the time that we gave you all to do the task on Friday, majority of you all managed to get the concept right and do the task, but there is some confusion regarding the number of times to make function calls to the generator function. So the special thing about a generator in Python is that there's a yield statement. So if you define the generator function, like what we told you to do in the problem statement, this will just initialize G to be the generator. It won't actually return you the values of X and Y yet. You need to call the next function for it to give you the next batch of data. And some people didn't exactly get how to vary the number that you put into the generator function, in this case n, which was set to be the batch size, or how they should structure their control flow of the program, meaning how they should do their for loops, etc., in order to distinguish between the 3 types of gradient descent that we taught you: stochastic, batch, and mini-batch gradient descent. So it is important to know the difference between these 3. Stochastic gradient descent means that you do a gradient descent step for every single training example. That means that your n will be 1. So every single x and y that generator will return you is therefore like a pair of x comma y. If you were to do batch gradient descent, then let's say you will set gen as 64, and then within one epoch you will only make one call. You will only make one call to gen, and then do your gradient descent step at the end of the epoch. That means one epoch you pass in the entire data all in at once. So this, I think Yi mentioned previous lesson, that batch gradient descent is good. You actually want to increase the batch size as much as possible, because that will allow you to approximate the entire data set at once, and therefore allow you to always move towards a minima, be it local or global minima. But the problem is when your ML tasks become exponentially more complex, so will your memory requirements. So most of the time, what we see in the real world is mini batch gradient descent, where the data is split into multiple batches, and within each batch you do one gradient descent step. So if you were to implement mini batch gradient descent, then it will basically be equivalent to having 2 nested for loops, with the outer for loop being the epochs, the for loop that counts your epochs, and the inner nested for loop being a for loop that counts the number of times that you want to make calls to the generator function so as to fetch your mini batches, over which you will perform gradient descent. So mini batch gradient descent, when I go through the recommended solution, then you guys will also get to see what it looks like in code. Okay, so yeah, this part is gone through. Then we also notice a bunch of you hand-coded the partial derivative functions, which is okay in this context because our linear regression project is very simple. However, when we get into more complex algorithms like linear classifier, which I think it is going to teach on Friday, or logistic regression. Regression that makes use of the logistic family of functions, which is like the sigmoid, the S-shaped curves. Those things, your differentiation will start to become like extremely complex. So that is why we actually advise you to use TensorFlow inbuilt functions like gradient tape, which we also saw some of you are using, because the reason why it's called gradient tape, as mentioned on Friday, is because it kind of tapes or records every single mathematical operation that you perform on the tensors themselves, such that it will build a computational graph of the operations that you perform on the tensor. So once you know every action that you've done on the data structures, then you can find the corresponding derivative of that action. For example, if you divide, then you know to use quotient rule. If you multiply two things together, you know to use product rule to differentiate it, etc. So that's how you'll do auto differentiation for you. Makes it much simpler. So okay, that is for task 1. Then after you all finish task 1, we ask you all to generalize the task 1 model for d-dimensional data. So some learning points would be, some of you were confused about the shape or the dimensions of the gradient m and the vertical intercept c. So for the linear regression case, it's very simple. Both m and c are constants. We are very familiar with y equals mx plus c. However, once we have d equals 2 problem, actually the correct answer would be m is a vector that contains 2 elements, while c is just a scalar. So that means that you will be regressing m subscript 1 and then m subscript 2, while your c is just one constant. The reason why we don't want a c subscript 1 and a c subscript 2 is because essentially that would mean that we are regressing 2 separate lines. And that's not true, because we have one pass to model. You don't want 2 separate lines. You want one line that fits the dimension of the data. And that's why m is a vector of shape d bracket, while c stays as a scalar. Okay? And once we bring in generalization to d dimensions, we expected to see vectorization, meaning that you all would take advantage of the flexibility that TensorFlow gives you with performing batch operations on the entire matrix or the entire vector. But some of you all still iterated through the tensors one by one. So for this kind of baby linear regression project is okay, because the train time is negligible. However, when you start to do computer vision, start to do NLP, then this is highly unadvisable, because actually your GPUs are specifically optimized to do batch matrix multiplication operations, and therefore you shouldn't be kind of wasting the potential by doing everything one by one. You call it vectorization or parallelization of the operations. So that's for task 2. Okay. Then for task 3, we ask you to implement L2 regularization for f subscript theta for your model. So for those of you who have forgotten, I can just go back to the concise summary. The L2 regularization, the act of regularization aims to add terms to the loss function so as to force the model to optimize in a certain way that you desire. So because like the math is just a language for you to codify what you want the model to do. So in this case, by adding lambda times this double bar theta to the loss function, you are adding an additional penalty. So this is an additional thing which the model will need to learn to minimize if it wants to do gradient descent. So L2 here, it comes from this double bar thingy here, which refers to L2 norm, which is Euclidean distance, the Pythagorean distance that you all are familiar with from secondary school, the one where you have a right angle triangle, and you find the hypotenuse, so it's a root of a square plus b square, that thing. This is L2 norm, we call it L2 norm. And essentially by adding the L2 norm of a certain parameter to be regularized, you are essentially telling the model, hey, if the weights that if this certain parameter has weights that are very big, then what's going to happen is that the Euclidean norm of the parameter is going to become big, and that's a bad thing because you want the loss to be as low as possible. So the model will be forced to keep the magnitudes of the theta that you choose to regularize close to zero, and this helps to prevent the model from having weights that are very big in certain areas and therefore causing it to bias towards certain areas. Okay, and in this case, linear regression, we have two parameters. One is the m, which is the gradient. The other one is a c, which is a vertical intercept. And you should only regularize the gradient because if you think about it, a line, the slope is controlled by the gradient. The vertical translation is controlled by the y-intercept. So that means that once your y-intercept is roughly around the correct value, actually most of the mean square error or mean absolute error is contributed by a wrong slope of the line. And therefore, it would make more sense to kind of simplify your entire process by only regularizing the m. Okay, so this is also highlighted in the Marcus report. It makes more sense to regularize m rather than having to regularize m and c as well, because for regularization you need to have a regularization parameter called lambda, and actually this parameter is a hyperparameter. It's something that the machine cannot decide using gradient descent. Lambda must be decided by the developer, and depending on different levels of lambda, you can get different model performance. So if you were to do regularization on both theta 1, which is the gradient, and theta 2, which is the y-intercept, you essentially have two lambdas to work with, and you're kind of creating work for yourself for nothing. And therefore, it makes more sense in this case to only perform regularization on the first parameter, the m. So we saw some of you doing regularization over c as well, so that's wrong. Okay, so that is the end of the Marcus report for the linear regression project. Now, what I'm going to do is go through the recommended solution. So as we go through the recommended solution, another learning point would be that of code readability or sectioning of your IPy notebook. Actually, this recommended solution, it should be shared with all of you. Yeah, so all of you can access it. So if you want to look at my screen, so go ahead, or if not, you can look at the code on your own as well. So what we noticed a lot of y'all doing when you're coding is that you were defining your gradient descent function and having your code basically below that gradient descent function executing the main thread. So this is okay for a simple linear regression, but in the future, we will highly advise you to use object-oriented programming. Object-oriented programming, because the name says object-oriented, therefore it allows you to have much greater flexibility in the kind of data types that you want to work with in your program. Typically, the data types that we are familiar with include things like integers, numbers, strings, characters, floating point values, or arrays, lists in Python. Object-oriented programming allows you to define your own classes, define your own data structures, and underneath each class, define your own methods to basically outline in code how your data structure that you define can be interacted with, how it will behave, and what capabilities it has. So in this case, what we've done is, okay, here we have all our useless imports, okay. What we've done is we define a class simple model. So we define a data structure.
Sorry, Alistair.
Yeah.
I don't think we have access to the...
You don't have access? That's strange.
Yeah, to the code. You shared with us last time, but it says you need access.
Wait, I can access though?
You are...
Wait,
But it says you.
Okay, how about this? I can just pop a invitation to you again.
Okay, thanks.
Could you send one to me too?
Oh, we share. Oh, you come.
Yeah, it shows that you share with us, but like when we use the link, it says you need access.
Bruh.
Wait, I think can now.
Okay. Anyone else got a problem? No. Okay, I assume no problem. Okay. So in here we define our simple model class. Then with every single class that you define, there always must be a constructor. A constructor is defined as the function that will create the class. When you try to instantiate a new copy of this class, the constructor will be called. So this function, double underscore init double underscore, is a reserved name for the constructor of a custom class. Yeah, and it will be called when you initialize a new copy. So in this case, what ECS has told the constructor to do is, when you create a new copy of simple model, you need to pass in the dimension of data, the learning rate, and the regularization parameter. So he will set self. Self is also a reserved keyword that refers to the current object. So in this context, self would refer to the current simple model object. So what he's doing here is, if you do self.w, that means that you are creating an attribute of the current object called w. In this case, w stands for weights. Then he just initializes to a variable of dimension d. Remember, because task 2 told us to generalize the model to dimension d. And the weights will be randomly initialized according to a normal distribution. Yeah. So some of you, I think Marcus also, your preset your weights and biases, and it's also not visible. It's either you put them to 0, or you just randomly fill them according to a popular distribution. Because if you were to arbitrarily select your values, your initialization values for your weights and biases, you may or may not be creating unnecessary gradient steps for yourself. So because, humans, you have no idea how to visualize the hyperplane, the lost hyperplane, right? And that's why you just want to, people just arbitrarily assign the initial values according to these kind of random distribution functions. Okay. Then for, yeah?
Okay, where did I get the D from?
D is a parameter that you pass into the constructor.
Oh, okay, thanks.
Yeah. Then bias also initializes it to a constant. Remember, because earlier on we said the C, the 1 in the set, must be a constant. So here you just put it 1. And then you set your self.learning rate equals the learning rate that you pass in. And your regularization lambda, which is the regularization parameter, which is the lambda that we mentioned about over here, we set it to the thing that you pass in as well. So this is the reserve method for the constructor. Okay. Then he defines a method under simple model. So step will therefore become a function that can be called under simple model. So it will be simple model dot step. That means that you will actually be calling this step function. Okay. Then for step, that means apply the gradients, do the gradient descent step. So in this function, he basically makes the changes to self.weights and self.biases. So he assign add is basically the same thing as you make the change, you make the mathematical operation, and then you assign it straight away to the variable. It's an inbuilt TensorFlow function. So again, we're familiar with this. Negative sign is there to indicate stepping in the direction of decreasing loss. Here you have your partial loss, partial weights, partial loss, partial bias, and multiply by learning rate. So this is a step function to actually do the gradient descent. Then he has a predict function to return the inputs times weights plus bias. And note that the dimensions of the input x and self.w were also not specified. They can grow to any dimension t because we have specified it over here. So that's why that's why this code, if you use OOP, use object-oriented programming, it's like more versatile than if you will have to hard code each of your examples, each of your functions. Like I see some of you doing in your notebooks. Okay, so this is his predict function. Then here's a
Wait, like, what's the difference between assign sub and assign add?
Sorry?
Like, what's the difference between assign add and assign sub?
Assign
Cause
sub.
I actually use both, and then I go for both work.
Assign sub. Okay, I'm not sure about assign sub, but I would guess that it's making a substitute. I think they're the same. In this case, they're the same. I'm pretty sure they're the same. But
Okay.
I think you can always Google that later. I'm not sure about assign sub.
Okay.
Then he has a train function. You make a train function, and in this case, he passes in the generator as an argument. So you don't need to fix whatever generator you're using. You can always dynamically pass it in as an argument. The number of epochs and steps. Okay, so if you want to introduce the concept of steps, then you have to go back to what we said about batch and mini batch gradient descent. We ideally want to implement mini batch gradient descent. This is what people normally do. That means that, like I said, there needs to be two nested for loops. The outer one being a for loop for incrementing your epochs. The inner one will control how many times you fetch a mini batch. So in this case, terminology that people like to use is steps per epoch. So in this case, this is what steps means. Steps means steps per epoch. So let's say your steps is 1000. That means for every epoch, you will make 1000 steps. Meaning that you will make 1000 calls to the next of the generator function. You will fetch 1000 mini batches. You will perform gradient descent 1000 times in your epoch. So this is implementing mini batch gradient descent. So over here he's doing auto differentiation using gradient tape. And the persistent equals true is to ensure that it lives the values can live on outside of the tape. This context. Okay, so because gradient tape watches all the operations that you perform on the tensors, that will also mean that you need to do the prediction inside the gradient tape, so that gradient tape can keep track of what exactly you're doing, so that you can do the differentiation, right? So this was like a problem that Cheng Hao faced on Friday, if I'm not wrong. His predict is outside, and therefore the gradient becomes none because there's nothing to differentiate, because there's nothing to tape. Yeah. So your predict needs to be in there. Then afterwards, you compute the loss, which is the batched predictions. Again, he's doing parallelization because the predictions are all vector. It means you're doing matrix operations. You're not iterating through the things one by one. Okay. The batch predictions minus correct answers squared. This is your mean squared error. And then you do a reduce mean. Reduce mean is basically sum everything and then take the average. Yeah, that's the same thing as the formulas that we've learned. Then this is this part here, it is essentially our this small l. Okay, reduce mean. This is our mean square error. Then plus regularization. Self.reg is lambda, the regularization hyperparameter, times TensorFlow the norm, the L2 norm of weights squared. Okay, so this is essentially implementing the L2 regularization. Is analogous lambda times Euclidean norm of the weights. Then you calculate the loss. Then take your gradient, auto differentiate. You will assign it to self.w and self.v. You find partial loss with respect to partial W, and partial loss with respect to partial bias. After you get these two values, you can do your gradient descent step. And then this for loop will just keep on iterating. So make sense? Yeah, if there's any questions, now it's time to ask. Okay, I shall assume this. Oh, I heard someone unmuting. Okay, no. By the way, right, some of you have tasks on the server. So, timed out. Okay, never mind. Just go and kill your Jupyter servers. Yeah. Don't hog the GPU memory. Okay. This is just the generator function that he provided to you. So, once you define your class, now you need to use your class. So this is where we go back to the main thread. So let's say we do 2 epochs with a learning rate of 1 times 10 to the power minus 4. Okay, our batch size is 64, and in every epoch, we are going to request for 10k mini batches. For task 1, our dimension of the data is 1d, so d equals 1. And we let g equals the gen of the batch size, so here's the generator. Okay? Now, we use our class that we have created. Model equals simple model. So when we use this syntax, we are invoking the constructor of simple model. And as defined earlier, the constructor has taken, we ignore, by Python syntax, self always has to be the first argument of the method. So we ignore self, we look at from D onwards, we look at the second argument onwards. So the constructor told us it must accept dimension of data, learning rate, and regularization parameter. So here, dimension is D, learning rate is learning rate, and regularization parameter is 1 times 10 to the power minus 3, okay, or 1000. Then afterwards, you just run the train. You just run the model.train will essentially call this method that you have specified in the class definition. And once again, because it accepts 3 arguments, you have G, epochs in steps, and therefore you will also need to put in G number of epochs and number of steps per epoch. So as you can see, using object-oriented programming is much cleaner than having to define the functions manually and use all of them in the global scope, especially because once your programs become more complicated, if you just anyhow rojak all the functions in the global scope, you can easily confuse yourself, especially with overlapping variable names or etc. That's why we recommend that you, in the subsequent tasks, you try and emulate this thing. You emulate this kind of structure. And if you were to step through, let's say TensorFlow or PyTorch or Keras source code, everything is using object-oriented programming. Your usage of even this kind of library functions is also object-oriented programming. So tape is an object, and then gradient in a similar fashion. Gradient is a method that is under the tape object. Okay, so that is task 1. Then now, here he just used a matplotlib to PLT is pyplot to plot the approximated line. Okay, by using the model weight and the model bias. Okay, then now we move on to Gen 2D, which is the task 2, 2D data. Again, realize that M is now a vector that contains 2 items, while C is a scalar. And similarly, we generate the X of the shape batch size, 2. That means that your X would basically be consisting of 2 numbers. And let's say your batch size is 3, right? It means that your number will be like that. Your X will look something like this. The shape is the batch size, so it's like peeling an onion. The first layer, you have 3 elements inside here. The second layer, so we go 1 comma down, the second layer, you have 2 elements inside here. So this is what I mean by a shape of 3, 2. Okay, so that's our 2D generator, and of course, okay, this is just me testing stuff. I can do this. Then because the model was implemented with generalization in mind, meaning that he does not need to define a second round of gradient descent functions, unlike some of you, and you can just directly use the simple model class, as you can see here. Instantiate again, model.train. There you go, train. Oh, bro, I just activated my Google Assistant. Okay, and then you see his loss is training. Then afterwards, he just outputs the weights at the end. There you go. 1, 2, and the correct 1%. So that is the recommended solution for linear regression project. And so we're gonna close the linear regression project up, and we recommend that you take the time to go through each other's code, see where y'all can improve, go through our markers report, see where y'all can improve, and also emulate the object-oriented programming structure of the recommended solution in future assignments. So